What's up to you all pre-matriculants? My name is Abram and I know it for sure that you guys have been waiting for this show. It is a Triple M day. Mine it is Maths Monday with Dina. How are you guys? Let me know on Facebook. Dina, how are you?
I think I must change my name to Mina so we can make it a quad Monday.
Oh, I like that. So how is you, Dina, Mina?
I'm doing very well, everybody, and glad to be here to work with the very sharp grade 11s.
Oh yeah, and how was your weekend?
Too short, as always.
As always, there's no more time to play. Hey,
No.
even the teachers are also getting their learners ready. They spend more time. I've seen where I stay, around where I stay. Even on Saturdays, people are attending, and even on Sundays, I'm like, wow, yeah.
It's mid-year exams, so everybody's busy. Teachers are marking, students are studying. Very busy time of the year.
And one thing I must acknowledge is that it's not only the grade 12s, it's from grade 10s now. So it means even grade 11s have got more time. They don't have more time. They also need to work extra harder like the matriculants.
Absolutely.
Well, what are we doing today?
Well, the grade 11s, we're going to do that very exciting topic, trig identities, how to work with trig identities, how to prove trig identities, and just generally become better at working with identities.
All right, Mindsetters, I hope we're not going to trick you, but if we do, we have to help you. On facebook.com/LearnExtra, that's where I'll be chatting with you guys. Also follow me on Twitter @LearnExtra. Otherwise, we do have some links that will be posted on Facebook, the view link, and the download a link for your notes, and also test yourself a link. 2 questions whereby if you answer them correctly, all of them, you stand a chance of winning this awesome Casio calculator, proudly sponsored by Casio. I'll be announcing the winner later on the show. Now, last week we spoke about More Maths Dinner, if you remember, which is a cool app for mathematics. It is a nice app because we can challenge each other's mindsetters and see where we are in terms of ranking, who's clever than who. So all you need to do is to go to momaths.org, and your code is it's 0JRN. 0JRN. That is your key code as the grade 11s. But Dina is going to be telling us more about the challenge question, and I'll see you guys on Facebook and Twitter.
Right, let's begin at the beginning. Let's look at what our lesson's all about, and then I'll give you the challenge question, and then we'll do some examples together in preparation for those test yourself questions. So today we're going to work with 2 fundamental identities. Firstly, the very popular one, the sum of the squares, sine squared plus cos squared is always 1. And the second one, a quotient one, where sine theta divided by cos theta will always be equal to tan theta. So we're going to work with those 2. And then we're also going to prove identities using the fundamental ones, as well as working with sum reduction formulae, which we did last week, as well as all the algebraic properties we are aware of. Okay, so then if we look at our challenge question, you need to prove the following identity: sine cubed of 180 minus theta divided by tan of 180 plus minus cos of 90 minus is equal to cos squared 180 minus cos of 180 plus. So, challenge to everybody. Let's see if you can prove it. It's very difficult for you to give us the answer because you can either show that the left equals the right or the right equals the left, and maybe you should just post on your answer you've been able to prove it or you haven't been able to prove it. Then we'll see, we'll tally up how many have actually been able to do that. Okay, I want to start off today by looking at some of the equivalent forms which we don't often think about of this very popular sum of squares, sine squared plus cos squared equals 1. The first one is that we can isolate the cos squared, and if we're looking for the simplified version of 1 minus sine squared, it's actually equal to cos squared. And then we're also looking at just sine squared could also be written as 1 minus cos squared. So we often don't think that we can take both of these variations from sine squared plus cos squared. Now, another thing we need to think about is that sine squared plus cos squared is the sum plus 2 squares. And therefore, it does not factorize. I can't factorize that. So the sum of squares does not have factors. Very important. However, if you had to write it in this format, into that pink or that green format, then I would get 1 minus sine squared. And if you remember from grade 10, we looked at a lot of 1 minus a squared, 1 minus x squared, 1 minus b squared. It's the difference of 2 squares. So that 1 is a square, the sine squared is a square, and therefore that does have factors. So sometimes we may need to factorize 1 minus sine squared as 1 minus sine multiplied by 1 plus sine, or we could rewrite that product as cos squared theta. So we need to have our trig antenna really very sharp and tuned in to see what version of the identity I want. If I have 1 minus sine times 1 plus sine, I know that it multiplies out to 1 minus sine squared. But then that can also be written as one term, cos squared. So at times we may have these two factors together, which we may want to write as those two terms, or we may want to write it as cos squared. We must always be aware that there are these three versions that we are working with all the time. We could also have 1 minus cos squared as the difference of squares, 1 minus cos times 1 plus cos, and we could also have it as sine squared theta. So we need to be looking out for these various ways of being able to write exactly the same thing. Notice that I'm taking it from sine squared plus cos squared. These variations, it can be factorized, it can be reduced. Now, very important as well, if we write 1 minus sine squared and we get cos squared, if we looked at the additive inverse, if we looked at negative cos squared theta, then that means that this would become a negative 1 and that would become a positive. So it's sine squared theta minus 1. So this version over here, we could take the additive inverse. We also need to look out for that. Then we also have the additive inverse of this one, which would be a negative over here, negative sine squared is equal to cos squared minus 1. So we could have the additive inverse. And sometimes we're also looking at the additive inverse of our square one. So if we took sine squared theta plus cos squared theta equals 1, and we took the additive inverse of the left-hand side and of the right-hand side, then we would get negative sine squared, negative cos squared equals negative 1. So in that case there, we get another identity. So all these are versions of our fundamental identity, and that one won't ever change. Now, if you're going to look at your test yourself questions, there is one where I have asked you whether cos theta plus sine theta is equal to 1. So the sum of squares is 1. Is the sum of the linears equal to 1? And a follow-up from that would be, what about the cubes? Would the sum of cubes be equal to 1? Okay, is that true? So we should always ask the parameters that have been given, will they hold true in all cases? The exponent is 2. If I change the exponent to 1, is it still true? If I change the exponent to a cube, is it still true? And for everybody, that's not true, that's not true. So it only holds true for the squares. So the square root of each term is not equal to 1. And that's very important to know, because sometimes you can get into an exam or a test and you see cos plus sine, you think, oh, I know, cos plus sine is 1. But it's not. It's the sum of the squares that's equal to 1. Okay, so that sets the tone for your test yourself questions, which you can now go and try. And for those of you who want to look at an example, let's see question 1. Prove the identity that 1 over cos A minus cos A all squared is equal to tan squared A minus sine squared A. And the best way of handling any identity is always to work with the side that appears to have a lot more operations and a lot more work. If I look at both these sides, I think they've got equal amount of work. They've each got 2 terms. Maybe the left-hand side's got a square that I need to multiply out. So let's start with the left-hand side and see where we go. Okay, so my left-hand side, I have a bracket that I'm squaring. So just to facilitate my product, I'm going to write it out twice so that I don't forget. I find that my grade 11s forget a lot to get my oys, my outers and my inners, the product of the outers and the inners. So you forget that middle term as we talk, okay, that should be a minus, not a plus. Let's just fix that here. So we've got, okay, so if we multiply that out, we've got inners and we've got outers. So we've got a 1 over a cos squared A, and we've got a minus a cos multiplied by its reciprocal. What is a number multiplied by its reciprocal? Always 1. So over here, I'm getting a negative 1, and over there, I'm getting another negative 1. So I'm getting a negative 2 as my outers and my inners, and then my outside ones is plus cos squared. So I've got a fraction, and that's why earlier I said we need to get in tune with algebraic properties, because to multiply that out, I now have a 1 minus a 2 cos squared a plus a cos to the 4a. So I've added up my fractions, and I really don't have much more room for maneuverability, because that is really a trinomial, if I wanted to factorize that, all over cos squared a. Another way of looking at this would be to say, let's firstly, before we multiply out, let's just collect our denominators or collect our fractions by adding the two terms. And we now have a 1 minus a cos a, or a cos squared a, which I've got as, okay, actually let's, in the denominator I don't have, let's just do that again. So we've got here, common denominator is cos a. This fraction's got a 1. That fraction needs a cos squared a. And then I need to square everything, which lands up to be, if I look at this version now, I'm getting a denominator that's got a cos squared a, and I've got a numerator that's got a 1 minus cos squared a. Now from our notes, do you remember where are our notes? 1 minus cos squared a would be sine squared a, or 1 minus cos squared a is sine squared a. So have your notes next to you just to confirm. So 1 minus cos squared is sine squared a, and I am now squaring that. So it's actually sine to the 4. So I've actually been able to simplify it slightly better, in that I've been able to get it into sine squared a instead of having all these in terms of cos. Okay, but let's look at the right-hand side. I've been able to work with the left in two different ways. Let's have a look at where do we go with our right-hand side. We've got a tan squared minus a sine squared. Tan squared a minus a sine squared a. Right, grade 11's decision time. What do we do with tan? Now, the whole thing about simplifying trig expressions is that we would like to get them either into sine or cos terms, because we can get most identities into that format. Why? Simply because if we're adding terms, then we could add the like terms, and if we're multiplying or dividing, we could then work with like factors, or we could divide like factors as well. So there is a purpose behind the identity simplification. We're trying to narrow things down to have it either in terms of sine or cos. Now, when we've got squares, we would work with a square identity to reduce that into one term. But if it was tan, then I could actually say that I have a quotient identity, a fundamental identity that changes my tan into sine over cos. Because I've got a tan squared, I'm going to get the numerator squared as well as the denominator squared. So that's cos squared a. And then I'm going to minus sine squared a. Right, then I've got two fractions, so that's over 1. So this is going to be cos squared a as a common denominator, and I'm going to get sine squared a minus sine squared a times cos squared a. So all I'm doing is I'm adding fractions. You've got to be very good with the algebra in order to be able to add fractions and to be able to factorize, etc. So the reason you've done grade 9 and grade 10 algebra is really as a support structure for the trigonometry, which uses a lot of those algebraic properties, adding fractions, being able to factorize, being able to multiply brackets, all that kind of thing. So let's see where we go with this fraction now. Can you see that I have two terms in my numerator? And do you notice something special about this term and something special about that term? It's actually equal to sine squared A minus, okay, let's just go back there. Right, it's actually got a common factor of sine squared A. So if I take out sine squared A, what am I left with? This term I'm left with a 1 minus a cos squared A. Okay, so I'm really doing algebraic work here, but utilizing, in place of our usual x's or y's or a's or b's, we're actually working with trig terms. That's really all that's happening. I've added two fractions together, I've got a common denominator, I've made those equivalent fractions, and from the equivalent fractions there was a numerator that needed to be simplified, and it had a common factor, so I've taken out a common factor, and I'm left with a bracket all over my cos squared A. And now we see that in the numerator, I've got this 1 minus cos squared A, which grade 11s, if you've got your little notes next to you, you will see 1 minus cos squared A is the fundamental identity, but in a different version, in the sine version. So it's sine squared A multiplied by sine squared A divided by cos squared A. And that gives us our sine to the 4A over cos squared A, which is, if you remember, that blue version that we worked out. Here, it was a little bit complex in getting the trinomial out, because we would need to play a little bit with these and change them into sine, and that was quite tricky, I think. So it's easier to just take the bracket, first simplify the bracket, and then square it. There is always a decision-making in terms of whether we should expand or whether we should keep it in the bracket first. And I often tend to keep things together before expanding, because expansion oftentimes leads you to have to come back and factorize. So in this case, it was a good way, just keep it together. I think Abram's ready for a break.
I'm more than ready, hey. Thank you so much, Dina. And holla to all the mindsetters that are watching right now. Peter and Peter and all the with all the mindsetters that are watching from Chibasa Secondary School, Haka Kane, who's watching Lubembe with her mom, holla at you also, and to all other mindsetters, Nkosnati, Tato, Beauty, Lisiho, Apua Morgan, Sharon, and Sanel Mtamo. Holla to you all mindsetters. We'll see you after the break. Welcome back, Prematriculate. Welcome back, Prematriculate. I'm so happy, guys. You guys on Facebook are understanding, and you guys are enjoying the show. So it makes me happy. I can't help it, Dina. It just makes me happy. But I must remind you guys that the Mo Maths app, which when you go to momaths.org, you can register, join a group there. Your code as prematriculants as 0JRN. 0JRN. That is your code. See yourself, test yourself there, challenge yourself, and challenge other mindsetters. I'm also part of the groups there. I think I'm on number something, 1,310 something. So I'm still pushing, guys. So let's see who's on top. Dina?
Yes, welcome back, grade 11s. We're going to do another 2 questions around identities, but I'm going to really put something really nice in to make us think about these things a lot deeper, not just look at them superficially. And so I've decided I will introduce some reduction formulae and just test how we've integrated last week's work with today's work, because really sometimes that's how you'll see it in the exam. It's just the integration of the topics coming together. So this one's going to be a little bit more time consuming, because we're going to have to work through the reduction formulae before actually applying any of the identity work. Okay, so question 2, we've been given the following fraction, and we would like to show that this left-hand side, now this is a classic case where the left-hand side must equal to negative sine x. I know I'm going to leave that negative sine x, and I'm going to see how close I can work with that left-hand side to simplify it down to negative sine x. So we're going to start with the left-hand side, and let us always write left-hand side. And while I'm writing this down, just a reminder to all grade 11s, when you're proving an identity, you cannot state that this is equal to negative sine x, because your job is to go and show that in fact it is a true statement. So don't write it equals negative sine x, then simplify equals negative sine x, then simplify equals negative sine x. You're actually going to get 0 for that proof, because that is not a proof at all. A proof requires you to work with the left-hand side, simplify that, and then show that in fact it is equal to that right-hand side. So be very aware of your setting out. It does count for marks, otherwise it makes no logical mathematical sense. Okay, so the left-hand side, we have sine, starting with the numerator, sine of x minus 180 degrees. And I would like to know, grade 11s, what is the reduction formulae for that? Okay, I think we'll just work on the top here. We're going to say, we remember from last week that we first write down what the various angles are in the quadrants, minus theta, 180 plus theta, and 360 degrees minus theta. And we also said that we need to know where are the various ratios positive, and that's where they are positive. Now, x minus 180 is not in one of those quadrants. But you've got to be very sharp, grade 11s, and look for additive inverses. But that is the additive inverse of the actual angle, which means I've got a negative angle, because if you've got the additive inverse, you've got a negative angle. So if I had to rewrite sine of x minus 180, grade 11s, this is what it would look like as the additive inverse. It would be the negative of 180 minus x. Now it is in a form that I am familiar. And mathematics is about rearranging, rewriting the expression in a different form that is going to be able to be simplified. So we have a negative angle, and do you remember, grade 11s, what the rule is for a negative angle? It is a negative ratio. So the sine of a negative angle is the negative ratio of 180 minus x. Now, grade 11, sine of 180 minus x is second quadrant. Sine is positive in that quadrant, so that would be positive, but it's got a negative here, so therefore that would be negative sine x. Look how much work there has to be before we get that negative sine x. So the left-hand side, we will start with a negative sine x as my first factor, and I would like to put that in brackets so that I don't get confused later and start adding things. And then I have this tan of 360 plus x. Describe what 360 plus x looks like. Describe where the terminal array will be. That's just an angle that's larger than 360 degrees. So for those angles, there's no thinking about it. It's always equal to the tan of the x value. Okay. Same, whatever x value you have, that will be the tan of that x. And then we have a division by tan of negative x. Explain what negative x is. A negative angle. So tan of negative x, the rule for all negative angles, if I remind you about that rule. Let's look for an empty page. I think we've got an empty page. Maybe there. Okay, there we go. Okay, so if we look at the negative angles, sine of negative a is the same as the negative ratio of the additive inverse. Change the angle, change the angle, change the ratio. Okay. Then we have tan of negative a is equal to negative tan a. Change to the additive inverse, change the ratio. And then the one that stays the same is this negative cos a. And grade 11s, the best way of remembering that you change the angle and the ratio stays the same is to remind yourself of our cos function. So when you draw the cos function, your cos function is symmetrical about the x-axis. So if I take 60 degrees and I look at its ratio, when I take the additive inverse on this side, look what happens, grade 11, the ratio is exactly the same. Doesn't change. If I take a value over here and a value over there, the additive inverse, the ratio doesn't change. So the cos function, I like to think of it as symmetrical about this line. So the symmetry of the cos function helps us to understand that the ratio that I get, if my angle is different, if my angle is the additive inverse, my ratio stays the same. My ratio doesn't change. So why does it change for tan and sine? Well, because if we had to draw their functions, and this is 0, then my tan is going to increase over here, but what's it doing on the other side? It's negative. And what about the sine? My function increases there, and what happens on this side? It does this. Okay, so sine is not symmetrical about the y-axis. Tan is not symmetrical about the y-axis. Only cos is symmetrical about the y-axis. And that symmetry helps us to understand that if I change the angle to the additive inverse, no change in the ratio. Whereas with the tan, it changes ratio, and with the sine, it doesn't change ratio, it actually changes the sign, because you'll see these are increasing that way, and these are coming this way, and those are increasing that way, and those are coming this way. So they're exactly the same ratio, but the sign changes, the sign changes. So that's a lovely way of reminding ourselves what the sine, tan, and cos of negative angles are. If you change them to the positive angles, then there is one ratio that stays the same, and that is the cos, because of its picture form. And if you're a student that learns in pictures, then this is a really valuable way of remembering that. The other way of remembering it is it applies, it follows the same rules as quadrant 4. So quadrant 4, you change the angle, the ratio stays the same, tan's negative, sine's negative. But you've got to find your own way of reminding yourself, how do you treat or how do you deal with negative angles? Okay, so going right back to where we were. Let's go back there. And I think we were over here. Yes, we were. Okay, so tan of a negative, having said that, cos is the only one that stays the same. So tan will change to negative tan. It's a negative ratio, put it in brackets, as many brackets as possible. Let's not change the function. And then we have this tan squared of 180 minus. Okay, a square function, whatever the ratio is, it can be positive ratio or a negative ratio. If we square that positive or negative, the outcome in both cases is that it's positive. So I actually don't have to think much when my function is negative. I can just write straight away that that is just going to be tan squared y. Be very careful, there's a different angle happening here. And then I've got this minus 1 over, again, I've got a cos squared. I don't even have to think about it. It's just cos squared y. Because when my function is squared, if it was a negative, which in this case it is, and it is a negative, which in that case it is, take the square of the negative, and we're going to turn it into a positive. Okay, so now, if you look at it carefully, I've got that times that divided by that. So that goes in there once. This negative divided by that negative would make it a positive. So I'm landing up to have a sine x, and I'm dividing it by this big bracket, which has got this tan squared y. Now this tan squared y, what is a fundamental identity that changes tan into sine and cos? It is our quotient, but because it's a square, we're going to have sine squared y divided by cos squared y. And we've got this minus 1 over cos squared y. Notice I very carefully have strategically placed this division, and I'm keeping it. Grade 11s, many of you try too quickly to find the reciprocal and then you get it wrong. I'll only take the reciprocal when I've got one term. So let's wait till we get to that one term. So that is equal to sine x divided by, and we have a cos squared y, and we've got a sine squared y minus a 1. Okay. Now, I have got this division, and I've got one fraction. Okay. And by the way, grade 11s, you cannot take the reciprocal of those two, because in you taking the reciprocal across a subtraction, I need to have one fraction before I can take its reciprocal. A lot of errors are made at this stage where people take the reciprocal or incorrectly. So I've got one fraction. When can I take the reciprocal? One fraction, so I can multiply it by cos squared y over. Now, what is sine squared y minus 1? Have you been listening since the beginning of the show? What is sine squared y minus 1? It is the additive inverse of negative cos squared y. Okay, some of you are wondering, where does that come from? Okay, it's the fundamental identity, and it's one of those versions that we saw at the beginning. I think they were over here. Okay, so sine squared y minus 1, here we are, sine squared theta minus 1 is equal to negative cos squared theta. You don't have to remember all the versions. You just need to remember sine squared plus cos squared equals 1. And then if you work with it as in terms of 1 minus cos squared or 1 minus sine squared, it's equal to cos squared. But if you've taken the additive inverse, then you've changed those signs. And grade 11s, that square identity must be doing its little cartwheels in your head in terms of the cos squared, the sine squared, or the additive inverses. You must be looking at those, because if your mind is stationary, then we're not going to get anywhere. So it's one of those original ones we had, and I think we're over here. Yes, we are. And we now have that sine squared minus 1 comes from where? It comes from our fundamental identity. Oopsie, not x. Sine squared x plus cos squared x is equal to 1. That's where it comes from. If I take a 1 minus sine squared, I get cos squared, but if I invert it, I get to negative cos squared. And that's where that negative cos squared comes from. So I actually get a negative 1 over here, which becomes negative sine x, which is equal to, and then you say the left-hand side is equal to the right-hand side, and you don't have to rewrite it. In mathematics, we accept that you've now proved that the left is equal to the right. Okay, so that was that one. Okay, the next one doesn't have much reduction formulae, so it looks like it's a straightforward algebraic process. You've got to be very good at algebra, adding fractions, factorizing, all there in getting us to simplify these identities. So we're not just reproducing fundamental identities, we're actually utilizing the identities in order to use some algebra to get us to negative 1 over cos x. Again, the left-hand side is a very complicated one. And in this case, I have one fraction, and I've got a second fraction that's got a denominator with a tan x. So I'm going to leave that hanging for a little while, because I want to see what happens if we represent tan x with its quotient version. So again, left-hand side would be going to leave the cos x and the sine x minus 1, and we're going to subtract this term here, which is 1 divided by, and then it's got this tan x, which I'm now going to rewrite as sine x over cos x, and I'm going to minus 1 over sine x times cos x. Okay, so let's see what happens. We've got fractions to add up here first, because I want to divide 1 by that, so I can get a nice fraction out of that, and then I'll see what's happening over here. So sometimes things wait until they're ready. We don't have to work on everything all the time. We can just wait. Sine x minus 1. Minus 1 divided by, and we've got common denominator, sine x cos x. This fraction is missing the sign, so I'm getting a sine squared x. This fraction over here has got everything, so it's a minus 1. And now you should be shouting from your couch. You should be saying to me, ma'am, sine squared x minus 1. I know what that is. It's the square identity, but in the additive inverse form, because we've just done it in the previous question. Look how repetitive things are. Sine x minus 1 minus this 1 multiplied by the reciprocal of sine x cos x over the negative cos squared x. So this is my fundamental identity into cos squared x. And if I now keep simplifying, I get cos x over sine x minus 1 minus, what am I going to minus? Well, this cos can go into that cos, so therefore I'm left with a negative sine over cos. So I'm left with a negative, which makes that a positive, sine x over a cos x. Okay, so I had a denominator that needed some simplifying. I've simplified it down to that. And if I keep going now, I have now 2 fractions, common denominator grade 11s. One fraction has got a binomial as a denominator. The other one's got just one term as a denominator. This fraction needs cos, so I'm getting cos squared x. This fraction needs the sine x minus 1. So we're left with cos squared x plus sine squared x minus sine x. And we've got that all over. Notice I'm not going to multiply at this stage. I'm hanging on to see what is happening in the numerator before I multiply out. So I get, grade 11s, you should be shouting. You should be seeing what this is. There's my square identity with 1 minus sine x. I'm now left with a 1 minus sine x. And in my denominator, I've got sine x minus 1. And you should be spotting that. What is the relationship between these two? One is the additive inverse of the other. So if I take out a negative sign from the numerator, I'm left with sine x minus 1. All over that bracket, sine x minus 1 multiplied by cos x. And look what happens. That bracket goes into that bracket, and we're left with minus 1 over cos x, which if you remember, it was exactly the same as the right-hand side. And I think Abraham is squealing. He wants a break.
Yeah, hey, even the mindsetters, they really want a break. They're saying, yeah, we've been counting. This is very, very long. I hope you guys are understanding, though. But if you're struggling, I'm here to help you. Go to facebook.com/learnextra. I'll see you guys after the break. Welcome back, you mindsetters. Now, this is the moment that we've all been waiting for, to hear the winner of our last week's Test Yourself question. And the winner is Sipho. Congratulations to Sipho.
Woo!
Yeah, Sipho. You, Sipho. So if you're the Sipho, we're going to call you. Congratulations to you. But otherwise, we have these comments before I give it back to Dina. Dumelo is saying, I just want to say good luck to all the grade 11, my classmates at Klabi High School. Tomorrow, may you start your exams with hope and make yourselves proud. And thanks to Learn Extra, I can't wait for my exam paper. Love you all, guys. All the best, guys. And to everybody that is writing, all the best.
That's wonderful. Lovely messages there, grade 11s, and fantastic, Sipho, that you were able to get that calculator. That's lovely. I'm hoping that many of you would have tried out, and if you didn't get it this time, next time. Okay, there's always hope. In my language, you say esperanza. That's hope. So I'm also teaching you a new language while I'm teaching you mathematics at the same time.
Esperanza.
Okay.
How do you, okay.
Esperanza.
Okay.
Yeah. Right, the challenge question. How many of you have been able to get the challenge question out? Abraham, how many have been able to get the challenge
I don't know
question?
if they got it right though, but I have answers, so I'll give you the feedback after
super.
answering. But there's so many. There's also a bit of drama that is going on about the challenge question. Some mindset are saying we haven't done this at school, we haven't covered it. That's when I say you guys need the notes.
You need the notes, and that's what we're here for. We're giving you a head start so that when you get to class, you'll be super smart and your teacher will really be impressed with what you know. And then she'll want to know, where have you become so smart? And you'll just have to say you learned it from Learn Extra. So isn't that fantastic? We really hear some of the notes may have gone too fast, but just go onto the site, Go and download the notes, go through them carefully, and you'll see how much sharper you'll be, even though you haven't yet covered the work. Okay. Right, so the challenge question included a little bit of that reduction formulae, as well as trying to prove that the left-hand side was equal to the right-hand side. Now, if we do an analysis of what's going on, before we jump in, we see that there's a cubic function, we see that there's a co-function, we see that there's a square function, and we see that there's a linear function. And it's very important, grade 11s, not to just jump and launch yourself right in, but to be able to analyze and to extract what the possibility or what the possible pitfalls could be, and not just jumping in with a quadratic identity if there's a linear and a cube as well. So let's be very careful while we step out and look at how to simplify the left-hand side as well as the right-hand side. Okay, so I'm going to start off with the left, and I'm going to ask you, what happens to the sine cube of 180 minus theta? Now, just to help us, and grade 11s, you should do this all the time, is to draw your Cartesian plane with where are the ratios positive, and fill in what do we call each of the angles, the terminal ray for each one of these. So it's 180 plus, and it's 360 minus. Okay, so now we have a 180 minus, which is a second quadrant ratio. So sine in that quadrant is positive, which means that sine cubed will also be positive. So we've got a sine cubed theta. What have we got in our denominator? We've got a tan 180 plus. So grade 11's position of my terminal ray, there it is, quadrant 3, and tan in the third quadrant is positive, so that's also going to be tan theta. Then I'm going to subtract the cos of 90 minus theta. What do we know about 90? 90 is the complement, they're complementary angles. So we talk about the Coco rule, and the Coco rule says that if angles are complementary, then we'll add or we'll take away the CO, the prefix CO. So we've spoken about this afternoon about how to deal with angles larger than 360, angles that are negative and the rules around them. And then finally, we've come to the cofunction. And you should expect to get each one of those as a reduction formulae. So the cofunction says, if I take the complement of the angle, then my ratio will drop the co. So it's currently cosine. It will drop the co, so we will land up with just sine theta. Okay, and let's just keep going as far as we can, because we now have sine cubed theta, and we're going to divide it by a tan minus a sine. What is the fundamental identity around tan? How can it be rewritten? Great, it's sine theta over cos theta. And we're now going to subtract sine theta. Now, grade 11s, from here onwards, you could actually say you don't actually need to have been taught the work at school, because this is algebra. Okay, don't wait for a teacher to teach you. This is asking you to take the cube of a function and dividing it by sine over cos minus sine. So there's a lot of algebra in here. And I can tell you right now, grade 11s, where it's going to go wrong is where you're going to try and change that division sign into a multiplication, and you're going to take the reciprocal of both of those. That's where it's going to go wrong. So if you want to take something away from today's lesson, take away that when you take the reciprocal, take reciprocal of one fraction only. So if I have two fractions, if I have 2, 3 fractions, I first rewrite it as 1 before I take the reciprocal. So priority is to actually say there's a bracket really around this. This horizontal division over here, we write it vertically like that. But if we had to write it horizontally, this is the same thing as sine cubed divided by sine theta over cos theta minus sine theta. And you may be saying that that means the same thing. Grade 11s, it doesn't, because the order of the order of operations is to do division before subtraction. So if we don't tell the sum to get its brackets around the denominator, we are going to get a different thing from what the original statement said. So when I write it vertically, I don't have to show the brackets because we understand that we must take the numerator and then divide it by the total denominator. When we write it horizontally, there needs to be a bracket around that because we want that answer first before we find the reciprocal. So that's where the pitfall is going to come from. So we have a sine cubed, let's go back to white, sine cubed theta, and we're going to divide it by one fraction first. What's the common denominator? Cos theta. That fraction doesn't need anything because it's over cos. That fraction's over 1, so it needs a cos. If that needs a cos, so does the numerator. So can you see that I get a sine theta times a cos theta? Right, so far I've got sine cubed theta divided by, now I've got one fraction. So in fact, I could decide to multiply by the reciprocal at this stage because I've got a times by a cos theta over that numerator. But can you see that that numerator includes two terms? And what do you notice is inside each term? Excellent. There is a sine theta in each one, so we can factorize. And if we factorize, we're left with 1 minus cos theta. So currently, I have the multiplication of these fractions, and it's very easy to see that sine cubed divided by sine theta gives me sine squared, multiplied by this cos theta over this 1 minus cos theta. Grade 11s, can we divide this cos theta by this cos theta? Is that possible? You should be shouting no. Everybody should be saying no, because this is a subtraction, so it means I need that answer first before I could divide the cos by that bracket. So when there are terms, I need their answer first before I can divide. There's an order of operation, and the order of operations really prevents us from being able to divide that. So if there was a times sign there, not a problem. But the moment there's a minus, there's a term separating the terms. I need to add them together first, but because I can't, because they're unlike terms, I still can't divide. So don't get dragged into that. Okay, and so now, grade 11s, I need your help. We've got a cos, and we've got sine squared. Can we change sine squared? Is there a way of changing sine squared into cos? And you should be saying, yes, ma'am, we can change it into 1 minus cos squared. Okay, the fundamental identities helps me change sine squared into cos squared times my cos theta divided by 1 minus cos theta. And I'm now left with a 1 minus cos squared theta, which in our notes originally we said can factorize. It's a difference of squares, so it's 1 minus cos, 1 plus cos, and I'm multiplying it by cos theta over a 1 minus a cos. So the 1 minus cos cancels into that, and we are left with a cos theta into 1 plus cos theta. Okay, let's go and see what is happening with our right-hand side. Okay, our right-hand side, I've got a cos squared 180 minus theta. Where is 180 minus theta? It's second quadrant. But do you notice that I've got a squared function? So a squared function is just cos squared theta. And where is 180 plus theta? Third quadrant. What happens in the third quadrant? Cos is negative. Be alert. There's already a negative sign there. So it's going to be plus cos theta. So if we take out cos theta, we're left with cos theta plus 1. Let's check. What have we got on our left-hand side? Is it a cos? Yes, it's a cos theta multiplied by a 1 plus cos theta. Any questions, Abraham?
Yes, so many questions. The first one is from Beauty. Hi, can you please ask Dina, how did she get that -2 in question 1?
In question 1, I think it was there. No, it was there. Okay, it's just the binomial times another binomial. And when I multiply cos over 1 by 1 over cos, that just becomes negative 1. So that's a negative 1, and another negative 1 is negative 2.
All right. Last one, because of time. How do you know when to square it? Because I see you changed cos to cos squared out of nowhere. I'm lost.
Which question?
I think it's the challenge question.
Challenge question. Let's just go there quickly. When do you change? I think it's sine squared into cos squared. I think the question is out of nowhere.
When do you know when to square?
When to square. Okay, I didn't square anywhere. There's no way that I've squared anything. But what I did do, which I think is possibly the area where we finding difficulty, is this one going in there, because I had other factors around me that had cos, and so I had this sine squared that I could change into 1 minus cos squared. And then I could factorize into cos squared. So the terms around it are guides as to where you should be going. So if I've got things in cos, I should try and have everything in cos. If I have things in sine, I should try and get things to the common term, whatever that might be.
Okay. Thank you so much, Tina.
Cool.
That's where we have to end it.
Ah.
Guys, thank you so much. I know that some of you haven't covered this section, but we're here for you guys. We're always a step ahead, and make sure that you get our notes on learn.mindset.co.za. But for today, Mindsetters, we love you and peace.